reserved rights of various parties, including Northeastern Educational Television of Ohio, Incorporated.
How do you do, ladies and gentlemen? I am Julius Sumner Miller, and physics is my business. And our business today is the idea of center of gravity. A marvelous thing to consider, really, and fantastic in its consequences for the human race. Consider the following. I have here a double track, which is downhill to my left. Here I have a cylinder of wood, which, as you know, will go downhill, as any respectable cylinder should do. But here I have another geometrical form, and I put it at the bottom of the plane, and lo and behold, it goes uphill. And that's a strange business. Well, friction forces are holding it there, so you see, it goes uphill. And a proper understanding of this lies in an understanding of center of gravity. An idea we got first from Archimedes in about the 3rd century BC. Consider a stick, a meter stick. If it was a good stick, as I would like to have it, it would have to be uniform, homogeneous, and isotropic. Those are wonderful words to know the meanings of. Supposing the stick weighs 10 pounds, and I support it with 2 fingers like that. It is clear that each finger pushes up with 5 pounds each. 5 plus 5 is 10. The stick weighs 10 down. Indeed, if I move the fingers elsewhere, I still exert 10 pounds up, but in 2 places. Now, can I not find a place such as that right there, where I exert a force of 10 pounds up? And we are then led to say that all the stick is right there, all of it, and that's the center of gravity of the stick. Incidentally, I could use also the phrase center of mass, and I leave it as an exercise for you and your teachers to find the difference in center of mass and center of gravity. Now, I said all the stick is here. This suggests that there's no stick here and no stick here. And somebody says, but I see some stick here. And I say, all the stick is right there. And I could prove it. Let me put a clamp on the stick and support it somewhere remote from the center of gravity. If I do that, the stick tips. Obviously, anybody knows that. But if now I put another clamp on the other side and find an appropriate weight here, you will see an astonishing thing, that I can put the stick in equilibrium on the ground that all the weight is at the 50 mark. So, on the blackboard, it would look like this. Here is the stick. There is the center of gravity in the geometric center, and I have supported it right here with a weight hanging here. And I say that if we consider all the weight of the stick, W sub S, acting right there, then that weight of the stick times that distance there is equal to this weight times this distance here. And so we can find the weight of the stick without weighing it by assuming all the stick is right there. Now, to prove that you are right when your teacher does this, all you need to do, having done the mathematics, is to put the stick on a platform balance in such a fashion and weigh it. And an astonishing thing is discovered. A very astonishing thing, that the weight of the stick is exactly what you get, disregarding some little experimental error, exactly what you get by assuming all the stick there. Let's consider it further. Here is an equilateral triangle. If I put a pin through one vertex or corner and hang a plumb line on there, a plumb line is just a string with a bob on the end of it, and such a plumb line is always vertical for the observer at the place in question. And then I draw a line on that triangle. I say that the center of gravity lies somewhere on that line. Proof. Let me do this from another corner, such as, say, this one, which isn't broken. And we see that the plumb lines intersect at a place. This place is the center of gravity of this triangle. All the triangle is right there. Proof. I am going to put my finger right there, and the triangle will remain in a horizontal plane, which was announced by Archimedes, again, in the 3rd century BC, in a classical book which he wrote, entitled De Aqui Ponderantibus. See, concerning equal ponderousness. You can discuss this with your classmates and your teacher. So, the center of gravity of this equilateral triangle, for those of you who know a little geometry, is at the intersection of the medians, at the intersection of the angle bisectors, at the intersection of the altitudes upon the sides, reviewing a little bit of Euclidean geometry. Consider another triangle, an isosceles triangle, the center of gravity found in the same way. Or consider an irregular body, center of gravity found in the same way, the intersection of the plumb lines. Of course, the center of gravity of a uniform circular plate would obviously be in the very center. Now, in all of these illustrations, we have found the center of gravity to be where? Where there is some stuff. There's some stuff there. So the question has very intriguing complexion, because here, if I hang this up and drop a plumb line, it goes so. If I now drop another plumb line, it goes so, and we see a most remarkable thing, very remarkable. The plumb lines intersect where there is no stuff, right in here. And this is the center of gravity of this slab. Moreover, all the slab, all the plate, may be considered to be right here where there is none, which is a most astonishing piece of business. So the center of gravity of a system can be where there is no stuff of the system. This leads me to ask, where is the center of gravity of a donut? The center of gravity of a donut is in the middle of the hole. And if you cut out the middle of the hole, or cut out the hole, I have in my right hand the center of gravity of this donut, which is a very remarkable idea. Now, to show you the consequences of this, let's look at this rolling down business. The uniform cylinder rolls downhill. Its center of gravity is in the geometric center, along the long axis and in the middle. If we measure the height of the center of gravity above the tabletop, which I would call the zero potential plane, measure it there, then measure it down here, we would find that this is lower than this. Accordingly, the center of gravity has gone downhill, which introduces another very fundamental principle, namely, that the energy of a system tends toward less. So this goes downhill. The center of gravity has gravitated downhill. On this one, the center of gravity of this double cone, referred to as a cone of two nappes, N-A-P-P-E-S, beautiful geometry established by René Descartes, the Frenchman. The center of gravity of this double cone lies along this central axis and in the middle of this single base. So when I put the cone here, the center of gravity is so high above the zero potential plane, the tabletop, and where is it now? It is clearly nearer the tabletop. So again, the center of gravity has gone downhill, although it looks as if this is a crazy piece of business, that the cone, stuck a little by friction there, the cone appears to roll uphill. So the center of gravity, very important idea. More of an astonishing nature. Here is a cork stopper. Here is a cork stopper with a pin in it, and there's the head of the pin. Here is another cork stopper with a pin in it, and that's the point of the pin. And if I put these point to head in this position, if I can find that position here, and let go, obviously it will not stay stably. It will tip over. Why? Because the center of gravity is above the point of support, a condition that is not good for equilibrium. So what do? I put a couple forks in here in any way whatsoever, and then I put the point of the pin on the head of the pin, and there it is. Let me get this away so it doesn't hit the glass vessel, and we see an astonishing thing. Just look at that. Should not that fall off? It should. But why doesn't it? It does not fall off for this reason. The center of gravity of this system is below the point of support, which is another condition of equilibrium. Here's a good illustration of it. Take this little man, a little metal figure in the shape of a man who supports himself, you see, on the toe of one foot. And that's fantastic, really. He is very stable. If I tried to knock him off, oh, that just slipped there. That didn't really fall off because of the inadequacy of the center of gravity. Look at that. What must we say? We must say this, that the center of gravity of this man and his rod and the sphere system is below the point of support, which makes him stable. I say the idea of center of gravity is an astonishing one, as I remarked earlier, in its consequences for the human race. Consider this one, more of the same. And I hope you see that I am injecting into this program some elements of fun and jest, because, as I like to say, the intellectual process is usually very severe, so it needs some fun injected into it to make it a little more palatable. Here is a figure most stable for the same reason, the center of gravity below the point of support. Of now fundamental interest to us is such a program as I have here. Consider this block of wood. Square cross-section, cut askew on the bottom. It is so stable. I call your attention to a plumb line that is supposed to be inside at the center of gravity, and that plumb line falls inside the base. Now, let me put another block atop the original. I hope you see what has happened. I have raised the center of gravity and shifted the plumb line to your left, my right, so that the plumb line passes more nearly on the inner edge of the base. The system is now less stable. If now I put another block atop, it is obvious what the consequences are likely to be. The center of gravity has been raised, the plumb line is shifted further to my right, and may indeed fall outside the base. This makes the system unstable, as you will now see. Notice, the slightest displacement is likely to tip it over. So, if a system is stable, as we say in physics, what we mean is this. Any slight displacement from its position of equilibrium will still allow it to return to where it was. If it is unstable, as we have now, because the plumb line falls outside the base, any slight displacement will raise havoc with us. Watch it. And it tips over. You know what I am representing here. I am representing the Tower of Pisa, which I hope you know about historically, and I thought you would like to see a picture of it. In Pisa, in Italy, and I hope one day you will go there to see it for yourself. I say it is a most wonderful thing to contemplate. So, ladies and gentlemen, and boys and girls, we come to the end of our first lesson, let us say, on the great idea of center of gravity, the notion first established by Archimedes. And I thank you for listening. How do you do, ladies and gentlemen? I am Julius Sumner Miller, and physics is my business. And I should say, how do you do, ladies and gentlemen, and boys and girls? I am Julius Sumner Miller, and physics is my business. And our special business today is the subject of inertia. And I must make the matter, the idea clear, as follows. Here we have a block of wood at rest on the tabletop. And I ask, what does that block want to do? Answer, the block wishes to remain at rest. Supposing now I have double as much block, and I try in turn to put that system in motion. What do I discover? It also wishes to remain at rest. Moreover, it wishes to remain at rest twice as much, and therefore we say its inertia is twice as great. And so you discover at once that I have used the term inertia and referred to the idea of mass as synonymous. So mass and inertia are synonymous. And this is all tied up beautifully in Newton's first law, which says what? If a body is at rest, it wishes to remain at rest. And if it is moving uniformly in a straight line, that's what it wants to do. In English, simply, whatever a body is doing, that's what it wants to do. Let's look at Newton's Latin for it. Newton put it in Latin. Axiomata siva legis motus. Axioms, even laws of motion. Corpus omne perseverare in statu suo quiescendi, and so on. And in English, a little more within our competence. Every body continues in its state of rest or of uniform motion in a straight line, unless there are some forces to divert it. Consider now the following. Here you come on April Fool's Day, let us say, on a package, on two packages resting on the ground. Here is one and here is another. And you deliver, you impose a force on the one. I will, instead of with my foot, with my hand, and it experienced such a motion. The force produced a motion in the body of so much inertia. Now I try it with this one. Hardly as much motion. Why? This one is filled with rags, and this one with 2 bricks, and this one has the greater inertia. So, the measure of the mass of a body is its inertia. Consider now the 2 aspects of Newton's first law. A body at rest wishes to remain so. Here I have a heavy block of wood, a hole in it, and I put a dowel rod in the hole. The dowel rod constitutes the handle. How can I put that handle into the block? As follows. As follows. Notice what happens. I hit the handle. The block remains at rest, whereupon the handle moves into the block. That's the first law. The body of large inertia wishes to remain at rest. Let me pursue this in another way to demonstrate the second part of Newton's law. What did the second part say? If the body is in uniform motion in a straight line, that's what it wants to do. I start again. Now I come down on a firm block. The motion of the handle is arrested. The handle and the block were moving. And what does the block want to do? Keep moving. Whereupon it lodges itself more firmly on the handle. Thus do we demonstrate Newton's first law in 2 parts. Let me do this another way. Very pretty. Very pretty. I have a support and a weight W supported by a string and another string with a loop in it here, which I shall show you. Let me call this string A and this string B. I propose to do as follows. I'm going to pull on string B, the lower string. And I can break either string B or string A by invoking Newton's first law. If I pull suddenly on string B, W wishes to remain at rest, and B will break. On the other hand, if I pull gently on B, A supports W, already there, plus the force I impose. And I shall show you that exactly with this demonstration. Here is a string. Here is a hook. Here is a weight. and the upper string is supporting the load. Here is the lower string, and I am putting a little rod inside here so that my hand is not underneath should the weight fall. I am going to break the lower string. Watch it now, the lower one. There it is, I broke it. Now I am going to change the string. I'm going to change the string. And now I am going to break the upper string by pulling slowly on the lower one. Watch it now. Watch. We hope that breaks. Now, supposing it does not. One is led to say the experiment has failed. And I say, no, the experiment doesn't fail. I have failed to meet the requirements of nature. Watch. I'm going to break the upper string. There it is. And so we can be applauded for success. Consider another demonstration of the same. Here is an enormous weight, 16 pounds. Here is a string attached to it. If I pull on that string in a gentle way, I'll do it by hand, in a gentle way, the string can support the load. Now let me try to accelerate it. What does Newton's first law say? Body wants to remain at rest. It has enormous inertia. Watch it. Do you see? The string has broken. I shall have more to say about this when I talk about Newton's second law. The second law. Consider now another dramatic demonstration. An application of Newton's first law, because we must not escape the fact that these laws of physics, of nature, of science, have vast applications in plebeian things. A brick, a trowel. Cannot the craftsman, the bricklayer, utilize Newton's first law in this way? Notice if he hit his hand with the trowel, he'd hurt it. But he can hit the brick with absolute abandon and feel nothing. Inertia of the brick. Here is another classic, which I like to do because it is so dramatic. A sheet of paper, about 20 inches by 30. 20 inches by 30. 600 square inches. The load on each square inch is roughly 15 pounds. Atmospheric pressure at sea level. Therefore, about 9,000 pounds of air on that paper. That's enormous inertia. Proof. Here is a board, 1/4 inch thick. I put the board under here, and now I am going to try to put that enormous mass of air into motion by a sudden impulsive blow on this end of the stick. The impulsive view that people have is, oh, the whole thing will catapult. No, it will not, because that mass of air is at rest, and Newton said it wishes to remain so. Watch it. It did not move. It did not move. Fantastic. Now, remember, ladies and gentlemen and boys and girls, when I refer to this block being at rest, and then I say, what does it want to do? And the answer is it wants to remain at rest. I would not have you dispose of this as trivia, because it took the genius of an Isaac Newton to establish it. Nothing trivial about it. Consider another dramatic demonstration. Oh, this one is a beaut. Here is a vessel of water, and it has quite some inertia, and I put it on this paper, and I move it slowly, slowly. Remember, this has large inertia. It wants to remain at rest, and I am not trying to accelerate it too rapidly, and thereby friction forces hold it onto the paper. And so I pull more and more and more and more. We're in a little trouble because friction isn't right for me. But anyone in his right mind must testify to the prospect, if I continue in the manner I have been doing, the whole thing will fall down. But if I invoke the laws of Newton, the first law, which says it wants to remain at rest and will refuse to be moved by short-lived impulsive forces, watch it. Are you not surprised that it stayed there? Consider another, more application. Here is a vehicle, and here is a body standing upright in the vehicle. And now I want to show you that if I move the vehicle, The body is at rest with respect to it, and what does it want to do? It wants to stay there. Watch it. And so it did. And that's why when you accelerate a car rapidly from a standstill, your head is jerked back because of the large inertia of the head. On the other hand, if the car is moving uniformly, if I now suddenly arrest its motion, what will the block do? Well, the block was going straight, and that's what it wants to do. Oh, notice I accelerated too fast the first way. There it is, and the block tipped forward. A quick one for your inquiry. Here I have two vessels, and remember the subject is inertia. They each contain 1 pint. And let us say that one is filled with cream and the other with milk. So I have a pint of milk and a pint of cream. Quickly, quickly, which has the greater inertia? That's equivalent to asking which has the greater mass. That's equivalent to asking which has the greater weight. And some are led to say, oh, the cream, of course, because it's thick and sluggish and viscous. Oh, no, mistake. The milk has the greater inertia for reasons, of course, you see clearly yourself. The pint of milk weighs more than the pint of cream. Another demonstration of the inertia again. Here is a stack of coins. They happen to be Australian pennies. Why? Because they have larger inertia than US pennies. And now what can I do? With a thin blade, I can deliver a sharp, impulsive blow to the lowermost one. And what do I hope to see? I hope to see the whole stack remain unmoved. Why? Because it's at rest and wants to stay. There it is. There it is. There it is. And I just love that demonstration. Why? Because it is a classic revealing the beauty and strength and simplicity, in a sense, of Newton's first law. I want to show one more. Remember what the second part of the law said. I would urge you never to forget that the first law has 2 parts, which are rarely ever properly separated. I said a body moving in a straight line wishes to continue so. Here is a ball swinging in a vertical plane, in a vertical circle. I would remind you that at the instant in question when the ball is right there on the end of the string, its motion is tangent to the path at that place, and if I should cut the string or let go of it, the ball would not go radially outward, but would go instantaneously in a direction tangent. So, this introduces here in a passing way the idea of centrifugal force, which is a nasty thing to handle, and often much is said that is wrong. But if I let go of the string at the top, where will the ball go? Tangent. Watch it. There it is, tangent. Now, it is proper, before we conclude a program on Isaac Newton, to show you one of many photographs of Newton. A very important place this man occupies in the history of humankind. And I would hope that when you go to London sometime, you will most certainly go to Westminster Abbey and see where he is buried. And what does it say on that beautiful epitaph? Among other things, let men rejoice that so great a one has existed. So we are coming shortly to the end of the program. One final enchanting thing, an array of cups. If I put this heavy block on them gently, I can drive this spike into that block without the cups feeling anything. Why? Why? Because the block has enormous inertia. If, on the other hand, I drop it, it's going and it wants to keep going. There it is. And thus I conclude, ladies and gentlemen, a program on inertia. And I thank you for your attention. How do you do, ladies and gentlemen, and boys and girls? I am Julius Sumner Miller, and physics is my business. And our special business today is Newton's second law, the second law. Now, in an earlier program, we discussed the first law, and I showed you some dramatic demonstrations on the first part, a body at rest, and on the second part, a body moving uniformly wants to do that. Now we come to Newton's second law. This is a staggering thing in its implications and very, very difficult, really. But what students of physics learn somewhere in their course is that Newton's second law says F equals ma. And indeed, that's what it says. But that's powerful and not so easy. Let us see what Newton said for his second law. In the Latin, mutationem motus proportionalem esse vi motrici, but the Latin is a little old-fashioned, so if we look at the English, here it is. Change of motion is proportional to force applied and takes place in the direction of the straight line in which the force acts. So, let me demonstrate Newton's second law. Here I have two carts, a heavy one, a massive one, and a less massive one, and they are connected with a pseudo-spring, an array of rubber bands, which are called elastic bands, but which incidentally are inelastic. Now they are on wheels so that they move rather freely, but we learned earlier that this one has less inertia than this one. Now, when I pull them apart and stretch the spring between them, the same force acts on both. And let us see if we cannot at once predict what will happen. If we apply Newton's second law to the forces acting on these cars, clearly the big car will have a little acceleration and the little car will have a big acceleration. That's an obvious thing to speculate on. Watch it. I'm going to pull them apart. There is one and the same force acting on both cars, and you will observe that the smaller one gets going the faster sooner. Of course. And so, here is an expression mathematically that describes this. And what do we learn from that remark? We learn that the accelerations are inversely proportional to the masses. The bigger the mass, the less the acceleration. Now, this experiment with the two cars, very important for our concern later, because we will talk in subsequent programs about the energy possessed by each car and about the momentum possessed by each car, and we shall learn then that Newton's second law has enormous implications for later work in physics. Now, more about the second law. Here is a scale on which I hang a weight. And I don't care what the scale reads, it reads something. We say it reads the weight of the body, but I really don't know what that means. Nor did Newton, because as we believe, gravitational forces, the earth pulls on this, stretches the scale. But remember, even Newton said, I offer no hypothesis concerning gravitation. Now, do we understand it today? But anyway, this scale reads the weight of this. So I'm going to write Newton's second law saying that very fact. Here it is. F equals mg, where mg is the weight of the body. Now I'm going to accelerate this system upward. And I want you to see what the scale does. Watch it now. The scale read more. And so I have to add here ma. In other words, the scale reads not only the rest mass of the body, but an additional force which was required to accelerate it upward. Let me now start again in the zero position, the system at rest, the scale reading the so-called weight of the body, and let me accelerate downward. Watch it. The scale reads less, and so I write minus ma, mg minus ma. And this tells us a wonderful thing, because if I were to go to the edge of my roof and hold this like this, and then let go of it here, and the whole thing fell down toward the earth, a good question to ask is, what would the scale read during the falling? And the answer is obvious. Since the acceleration downward would be that of a freely falling body, the scale would read 0. So if I should jump off from my tabletop, while I am in flight toward the earth, I am weightless. I am weightless. Now, this second law bears on the first one, which I showed in an earlier program. You remember that I had an enormous weight here, on which I pulled gently with a string, and the string held it. But when I gave the system a sudden acceleration upward, the string cannot endure it. And I said then that the body wishes to remain at rest. I now add an additional fact, that the string must exert a force not only equal to the weight of the body, but an additional one to accelerate it, which it may not be able to do. No, it couldn't do it. Now, what is the meaning of this for other things? Supposing I had an enormous sphere, such as I have here, a steel sphere, 2 inches in diameter, and then a teeny-weensy one. And I want to show you that. I want to show you that. In fact, here I have several of different sizes. There's one. There's one. Very good. Now, I have one in here that is so tiny, in fact, that I can't see it without my glasses. That shows you how tiny it is. And I wonder, if I get the other debris out of the way, can the camera get that little one? Right. Right. Well, it's there. I assert it is there, even though you cannot see it. Oh, yeah, it's awful tiny. And what am I going to say about it? Supposing I hold these two, I won't hold the tiny one because you can't see it. Supposing I hold these two at the same horizontal level, above the level of the earth equally, and I let them go. They fall with the same acceleration. Proof. Newton's second law. Proof. F equals ma is the generic expression for Newton's second law. Now, what is the F acting on this body? The F acting on that body is its weight. And when I let it go, what is its acceleration? It has a certain mass m. Its acceleration is g. So these two equations, you see, this, the generic one, F equals ma all over the universe, so we think, and W equals mg for earth-dwelling creatures who wish to look at the weight of a body. So you can see that if I doubled the mass of any body, I would at once double its weight, and its acceleration remains unaltered, which is a sort of explanation why all bodies have the same free fall acceleration, as Galileo showed in the 17th century. Now, this is quite remarkable, because one is led to think, why? I can't believe that this one will not fall faster than this one, and this subject is taken up very excellently by Galileo in his dialogues concerning two new sciences, where I urge you to read the discussion between Sagredo and Salviati and Simplicio. Now, there are some further implications of the second law which have some levity. I like physics in cartoons, and here is a cartoon that I recently saw. Here is a little boy, and there is a bathroom scale, and here is another little boy, and they weigh, by all looks of things, about 70 pounds. Now, it's obvious what has happened. This one jumps down onto the scale. And what is the caption under the picture? Wow, he says, wow, 140. You can see that this is Newton's second law. F equals mg plus ma because of the force delivered through its acceleration to the scale. And I think that's terrific. Let's consider another such problem. Here is a smooth pulley fixed, say, to a solid beam up there. And here is a rope over the pulley. And here one man stands holding the rope. And here an identical weighted man stands holding this rope. And they are both on the ground. Question. The man A climbs the rope. B just holds on. He just stays there. Question, what happens to B? Answer, B gets a free ride. For whatever A does is felt by the rope and in turn by the man. And so, this is really Newton's second law. Two men on a pulley. Now, a more dramatic event. Much more dramatic. Here is a scale which reads from 0 to 2,000 grams, and I put 1,000 on it, and clearly the scale reads 1,000. If I put 2,000 on it, at rest, remember, at rest, the scale reads 2,000. Now what am I going to do? I am going to put the scale on a horizontal plane on that board in such a fashion with a pulley here and a rope and a pulley here and a rope, and I'm going to put 1,000 there and 1,000 right there so that I have 1,000 pulling to the right and 1,000 pulling to the left. I'm going to do that right now. There's 1,000 on the right, and I've got to hold that. Now I get over here and I put 1,000 on the left, and then I cover it over, as I like to say for my students, so that evil eyes do not see it. And remember now, we asked the classic question. When I had 1,000 on the scale in the vertical line, it read 1,000. When I put 2,000 on it in the vertical line, it read 2,000. We want to know, what does the scale now read? 1,000 pulling to the right, 1,000 pulling to the left. Several answers. One, oh, says somebody, it reads 0, since the forces annul each other. No, no, says somebody else. 1,000 to the right, 1,000 to the left, it reads 2,000. And I must tell you that whatsoever your point of view, these are both wrong. So, I could leave it as an exercise for you to do, but since I have a kind heart, I will tell you that the scale reads 1,000 grams. But having told you this, I urge you very seriously to explore why that is so. One further little comment. Oh, I want you to see another picture of Newton. I showed an earlier photograph in his later years, and here is one as a young man, 17 years old, when he entered Trinity College in Cambridge, a genius the like of which the human race has not yet again seen. One last experiment. Newton's second law. Here I am going into an elevator on the ground floor. The push of the floor of the elevator when at rest is my weight plus the weight of the bag. Now the elevator accelerates upward. You know what happens. Your knees buckle and the load is pulled out of your hand. No, 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 not pulled. It wanted to stay at rest. It was at rest, and that's what it tried to do. But what is the explanation of the added tension in my arm and the bending of my knees? Answer, F equals mg plus ma. Now the elevator is on an uppermost floor and starts down. You know what happens? Your belly feels empty. F equals mg minus ma. And so we have a better understanding of the laws that envelop us by applying the laws of Newton. And I thank you for your attention. How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business. And our business today is the very special third law in Newton's 3 laws of motion. And to view it at least once in our lifetime in the Latin, I have it here. Lex 3. Actione contrariam semper et equalam esse reactionem. Now, if you didn't know any Latin at all, you'd see something in there about action and reaction. And indeed, that's what it sums up to be. Third law, to every action, there is always an equal and opposite or contrary reaction, or the mutual actions of any two bodies are always equal and oppositely directed. Now, a strange introduction to this law would be as follows. Consider me standing still and quiet on the earth, and I jump up in this manner. I ask, did you feel the earth recoil? And the answer is, it must be, it did indeed recoil, even though you may not have felt it. Why? Here is the earth, enormous mass. Here I am, a teeny-weensy creature of little mass. I push down on the floor with a force F, which acts on me and on the earth. And as before in the second law, my little mass, you detect, has an enormous acceleration. Up I go. But the earth, having an enormous mass, has a teeny-weensy acceleration, which you cannot detect. So, consider Newton's third law in a toy. Here is a little vehicle with some wheels, to which is fixed a rubber balloon, and I blow some air in the balloon. Now I'm going to let the air come out of a certain hole, orifice here. The air comes out this way, and what must the vehicle do? The vehicle must go the other way. Watch it. There it goes. And so, I am reminded of a certain exercise that goes like this. Here is a rocket vehicle. We have some stuff in here in a state of combustion. The products of the combustion come out here. Millions of little particles of stuff. Now, many people have the distorted notion that this stuff coming out here must push against the atmosphere in order for this to go. And I say that is utterly erroneous. This system, this vehicle, works better where there is nothing, because we want the little mass of stuff coming out there to come out with the greatest possible velocity, and hence have the greatest rate of change of momentum, the product of m and v being momentum. Now, I'm going to go back to the two cars, because the case of the two cars, I said earlier, very important. Massive car, less massive car. I stretch the spring between them. One and the same force acts on both, and we witness an astonishing thing. Here is the massive car, here is the little car, less inertia, there is the spring. Now, what did we see? The same force acted on both. But you notice that the smaller one had the bigger acceleration, and the bigger one had the lesser acceleration, and therefore, in the same time of travel, and they would both travel the same time from time zero to the time of collision, clearly the smaller one has the higher velocity. So, writing the momentum of both cars, we would equate it as follows. The large car has a little velocity, the little car an enormous velocity, and these momenta are equal. Very important that you see that point, that the same force acts on both, the accelerations are inversely as the masses, and the momenta are equal. In another program, I will talk about their energies, and we will discover a very strange thing. Now, more on this conservation of momentum, which is essentially Newton's third law. Here I have a CO2 cartridge. Gas in here under enormous pressure. Here is a carriage in which I put it. I'll look around that end. And you will notice that there is a barrier on this end of the cartridge, of the carriage. Now what am I going to do? I am going to make a hole in this end of the cartridge. The gases come out this way. Oh, I erased that before. The gases come out this way, and they have a certain momentum, their mass and their velocity. The vehicle must go the other way. Watch it now. Watch. There it goes. There it goes. Miller's earthbound rocket. Now, a very important thing. It fled away. Fled away. Momentum, I'm sure. I would have asked a question had I had it in hand. Question. I would feel it to be very cold. Very cold. And I want to know, why is it cold? A second question. There could indeed be frost on it. And the question is, where cometh the frost? In the first question, we have a very powerful piece of physics. The gases coming out must do work. This costs energy. And I leave it there for further discussion in another program. Now, let's go to something still more dramatic. Again, conservation of linear momentum. Here is an array of steel spheres, highly elastic. Steel is highly elastic. By that I mean, when they are deformed, they recover. They lie in the lowest potential configuration. I take one up the plane, let it go, having given it some potential energy, and it collides with the system at rest, and watch what happens on the remote end. 1. Oh, that's terrific. Watch it. Look it. Nearly instantaneously. Indeed, I'm led to ask, how fast does the impulse get down there? Answer, with the same velocity as the velocity of sound in steel, which is about 15,000 feet per second. So if this were a foot long, oh, that's more likely a foot long. That's 9, 12 inches. Watch it. 1/15,000th of a second. You notice, too, that the whole system experiences some motion. That's because they all wish to seek a lower potential plane. Now, 1 at collision MV. 1 goes away MV. Watch 2. 2, MV plus MV, 2 MV. Now let us disregard the intermediate or the other motions that we witness, because a discussion of this would divert me from my purpose here. All I wish to say is that whatever the momentum before the collision, so that is the momentum after. 1, 1. 2, 2. 3, oh, notice they are seeking a lower potential plane. The energy of a system runs downhill. 3, oh, that's pretty. Notice they are seeking a lower potential plane. 4, watch it now. Notice they are seeking a lower potential plane, just as my energy is running downhill now as I do this show. 4. 5 up. 5. And so we say, without question, the momentum before the collision is equal to the momentum after. Consider another classical demonstration of mine, which is easy to do and quite dramatic. Here is a steel pipe. This demonstration I will call virtual, V-I-R-T-U-A-L. There are some demonstrations that I do for real, and I call them real demonstrations. This one we will imagine, and imagination is a very necessary ingredient of this business. We will imagine a steel pipe closed up tightly on one end with a cap, mounted on wheels, and in this chamber I put some dry ice, solid CO2. Then with a wooden plug, I plug it up very firmly, and I let it stand here on the table in the hot air of the classroom or the TV studio. And what happens? The CO2 sublimes, goes into gas or vapor. The pressure builds up more and more. The pressure gets enormous inside. Something has to go. What goes? The cap, with an enormous velocity, enough indeed to kill a man. So if you should do this, I warn you, have some caution. And what happens to the vehicle? It goes the other way. Big mass, little velocity, little mass, large velocity. Conservation of linear momentum. Powerful business, powerful. Consider toys have a large role in my business because the physics of toys is an enchanting thing to engage in. Toys, I would have you understand, ladies and gentlemen and boys and girls, toys are intended for child's play. but the physics of them is hardly that. Here is a little propeller with some inclined blades, and I have mounted it in a chamber wherein resides a spring. So I am storing some wound up elastic energy in the spring, and I release it. I did that one prematurely. What happens? How is Newton's third law? How does it play a role here? Answer. The pitch blade engages the air, drives the air down with a momentum mv. The vehicle must go up. Watch it. There it is. Oh, that's a pretty thing. And then it's spinning as a top, about which I will speak in another program. So the question is to be asked is, how does a bird fly? Here is a bird flying. Here is a bird. I'm probably viewed as a vulture. Bird, bird. I can only fly if I push the air down, and that's why I go up. Now, when a bird soars, as they do ever so gracefully, that is quite another thing, again, to be considered subsequently. Or a balloon. Here's a balloon. Incidentally, I'm going to do a program on bubbles and the like, and I will raise the question of why is it hardest to blow up a balloon at the very beginning and easier to blow it up the bigger you get it. But anyway, I've put some air in there. Now you know if I let the air out here, momentum mv, momentum the other way. There it is, like that. And one last exploration. One last exploration. Hero's engine. Here is a little vehicle you can make out of a tin can. You put some tubes through it and bend the tubes at right angles to their lengths. Put some water in here. Boil the water. The steam, more exactly vapor, which becomes steam on condensation, the vapor comes out the orifices, and this turns around ever so fast. This is a substantial demonstration of Newton's third law. And here is a bigger scale one on which we could run a very quantitative experiment. So much water, so much heat energy put in, so much energy gotten in the angular velocity of the vehicle. And so, what must we now say? We have explored in the passing shows the first law in two parts, the second law, which is wrapped up in F equals ma, and the third law, referred to as action and reaction, which I will close in this way. Here is a very freewheeling vehicle, and you know that if I stand on it at rest and go forward, the cart must go backward, which it does. And I say that when I walk this way, the earth goes the other way. I thank you for your attention. How do you do, ladies and gentlemen, and boys and girls? I am Julius Sumner Miller, and physics is my business. And on today's program, our special business is the subject of energy and momentum, two of the great immutable ideas of physics. And we must make clear their difference. So, for my purpose, I go to the two cars again. You remember what we have in earlier programs, a large, massive car on wheels, and a smaller car, little m, on wheels, and they are on the tabletop, and they are connected by a sort of elastic connection of rubber bands. Now, when I pull them apart, I store some elastic energy in the stretch spring, and there is a force then which is exerted on both cars. Now, what did we learn before? We learned that the big car has a little acceleration and the little car a big acceleration because one and the same force acts on both cars. Now, we also saw on another occasion that the little car acquired the greater velocity and the bigger car the lesser velocity, and we called the product of m and v the momentum. And it is not unreasonable now to say that because the accelerations are inversely as the masses, the velocities are so, and therefore the momentum of the little car is equal to the momentum of the big car. So their momenta are equal. But now watch. Watch. Is it not true that the smaller car went the greater distance? That is, if I let them come from a place of rest and meet, they would meet somewhere in here. This is the distance the big car would go, and this is the distance the little car would go. So the little car goes the greater distance. S, little s. And now I define for you what is meant by work or energy in physics. The product of a force and a distance. The product of a force and a distance. So, the same force acts on both cars, but for the big car, the distance is a little one, and for the little car, the distance is a big one. And these products are not equal. So we learned this astonishing thing, that although the forces are the same, the accelerations are inversely as the masses, the distances are inversely as the masses, the momenta are equal, but the energies are not. Very important idea. Now this business of energy, beautifully demonstrated as follows. Look what we have here. Here is a curved track, straight and short here, straight and long here. Now this end of the track is at the very same elevation above the tabletop as this end. I have shimmed it up on that end to get it horizontal. And what do? We put a ball at the top of this track at this end. It has so much potential energy, being so high above the zero potential plane, and I let it go. Now it is losing some of its potential energy, gaining kinetic, losing energy, really, because friction is in the system, and we hear sound, which costs the ball something. It cannot produce the acoustic energy for nothing. Now, what do some think? That coming down this long track, the ball down here will have enough velocity, enough kinetic energy of motion to put it up over the track here. But that is not so. If the system were absolutely ideal, no friction at all, which is impossible, the best the ball could ever do would be to go to the same height here. And since we are in a real world and friction plays a large role, the ball can never go as high on that end as I let it go from on this end. Watch it. Oh, it did. I'm glad it did, because I said it wouldn't. So somebody says, Professor, the experiment failed. No, I think what I have done, I manipulated this end a little improperly so that this end is higher, and therefore it did what it did. So you see, a lesson to be learned. Experiments never fail. I'm going to lower this a little, and now I hope that this end is the same height as that. Now watch it. Oh, that's it. And less, and less, and less, and less, and less, and so on until the energy of the system is spent in friction and in producing sound and in vibration. A very beautiful demonstration, a device which I call my energy track. Now, let's consider this business of energy further. Here is a block of wood. Here is a nail. I drive the nail into the block of wood. Oh, says somebody, what kind of physics is that? Astonishing physics. Why? I am doing work on the nail. The nail is doing work on the wood to separate its particles. And when work is done, when it is done against friction forces, heat energy always arises. Heat is a necessary consequence of work done against friction. It's proof. I'm going to pull that out. Oh, what do I feel? Too hot to handle. Accordingly, the work I did on the nail has been commuted to friction. Now, there are several kinds of energy. Several kinds which we need to consider. Mechanical energy. Mechanical energy. Thermal energy. I just showed you that with the nail heated by driving it in. While we're talking about thermal energy, here is some popcorn. Some popcorn. Now, you know that if you apply thermal energy to the popcorn, it soon, as a result of this application of thermal energy, of heat, explodes. Why? Because we gave energy to the little bit of water in the droplet, in the kernel of corn. It expanded enormously. How many times does it expand? Fantastic. 1,700 times. Isn't that fantastic? No wonder the kernel explodes with a rupturing force. Mechanical energy, thermal energy, acoustic energy. Sure, my vocal cords are in vibration, and that's the only reason you can hear me. I am giving rise to excitation of the air in this place, and it is falling on your eardrum and putting your eardrum into motion, and then the bones in the ear, and finally the impulse gets to your brain. Acoustic. Magnetic energy. Electrostatic energy. Electrostatic. Let me show you that, because it is absolutely exciting. Watch this. Watch. I have here some cork dust, which I put out on the table. Cork dust. It is lifeless and dead and inert. Here is a Bakelite hard rubber rod. Now the rod, I say, and later we will say more about it on a program on electrostatics, the rod is electrostatically neutral. I bring it near the cork dust, and what do I see happen? Answer, nothing. Seeing nothing happens is a very important thing to see. Very important. Now I am going to do some work on this rubber rod. Work, work. Now watch. Oh, mamma mia, look at that. The cork dust has been attracted to the rod. Not only that, but it's jumping off. It's jumping off. Oh, jup, jup. And would you believe it? This is the foundation of all of our electric science. Indeed, these television cameras could not work were this principle not uncovered. More about energy. More energy. Energy. Here is a massive weight which I have lifted above the level of the floor, the zero potential plane. I am doing some mechanical work on it. I am endowing it with potential energy. Here is a nail in a block of wood, and I release the weight. Look what has happened. It has driven the nail into the block. The heat developed here, very substantial. A toy, energy, a toy, a spring. If I do work on the spring, I store energy in the spring. There is a so-called suction cup on the bottom, and in another program I will show you that that word suction is not a good one ever to use, but I'm going to put a ball in this upper platform, push down the spring, storing some energy in the compressed spring. Now the energy is available to do work for me on the ball. When the atmospheric pressure seeps into that so-called suction cup, it will let the spring loose, and you know the consequence. Up will go the ball. There it goes. Up went the ball. And there was something else. There was some action taking place in this projectile mechanism, which bears also on momentum and energy. Consider this business of momentum. This gun is a toy, and so we need have no fear about it, but don't play with guns. Concerning momentum, if I shoot the gun holding it far from my shoulder, will it not kick very severely and hurt me? Why? The mass of the gun recoils with a certain velocity, the M and the V constituting a certain momentum. How do you avoid this kick? You hold the gun tightly against your shoulder so that when the gun recoils, you and the gun constitute a larger mass and therefore less recoil velocity. An excellent demonstration of momentum conservation. Consider a toy made for 3-year-olds. Here is a little toy, a teddy bear mounted on an elastic shaft through his shoulders. He stands in a vertical plane because his center of gravity is below his axis of support. And now what am I going to do? I rolled him away, and he rolls back. And so I am demonstrating a profound principle of physics in a toy for 2-year-olds. We stored some elastic energy. It was now available to do work on me to return the car. Or such a toy, an array of geared wheels and a shaft, and some feelers in there which rub against other things and produce heat from friction. And notice, I am showing the transmutation of mechanical work into thermal energy as well as into light, because when bodies get hot enough, they become incandescent. Energy, momentum, very important. Now, as one views the history of this subject, I invite you to study it yourself, because for 150 years, there was much dispute on the difference between MV and MV square, which was settled by a Frenchman named D'Alembert. But who gave rise to the problem in the first place? A young Dutchman by the name of Christian Huygens. And I want to show you a picture of him as a little boy at the age of 11, an enchanting little rascal. And I shall have more to say about him sometime on a program on light, because he spent his youthful days throwing pebbles into the canals in his native Holland and watching the ever-growing circles of disturbance, and thus was led to the idea of the wave motion of light. And here, finally, is a picture of him in his later days with his what shall we call it, wig. Now, the idea of momentum must be clearly distinguished from the idea of energy. And I thank you for your attention. How do you do, ladies and gentlemen, and boys and girls? I am Julius Sumner Miller, and physics is my business. And our very special business today is the subject of freely falling bodies and bodies which are projected, projectile motion. And I would remind you of things already learned in earlier lessons, such as, for example, a body of small mass, a body of enormous mass, released to fall freely, released simultaneously to fall freely. And what is their behavior? They fall at the same rate. And you remember, it is Newton's second law that tells us that, namely that F equals ma, or for freely falling bodies, W equals mg. Now, what is the action of a body falling freely? Of course, it encounters in real life some viscosity and friction and trouble with the atmosphere. So what we can do is lodge a heavy body and a light one, say a coin and a piece of paper, in a tube, and then with a vacuum pump, take out as much air as we can, and then do as follows, and we would see both bodies fall at the same rate. I had this tube originally evacuated, but there has been a leak, so the experiment, as some would say, has failed. But I remind you, I have not provided nature with her requirements to show the simultaneity of fall of both bodies in free space. Now, when we study a falling body, dropped so like that, we learn as follows. Supposing it starts right there. 1 second elapses, and we find it right there. How far has it fallen? 16 feet. Now we let another second elapse, and I'm not drawing this to scale. And how far would it fall in the second second? During the second second, it would fall 48 feet. Now let it fall for a third second. And how far would it fall during the third second? And we find 80 feet. And these numbers have some mathematical enchantment, because 16 divided by 16, 48 divided by 16, 80 divided by 16, and we see that the numbers are the odd numbers beginning with unity, which is a discovery that Galileo made in the 16th century. Now, further than that, you see that the first 2 seconds is 64 feet, the first second is 16 feet, the first 3 seconds is 144 feet, and look at these numbers. 16 into 64 is 4, that's 2 squared. 16 into 144 is 9, that's 3 squared. So the distances all fallen during the succeeding seconds are in the order 1, 4, 9. You see, 1, 4, 9. 1 squared, 2 squared, 3 squared. Now, when we study a freely falling body, it is too far to measure in real life. So what do? We have a machine which records a falling body and where it is every 60th of a second. And here is a tape which I have run, and the point to be noticed is that the distances as we go down increase in the order I have described, a discovery made by Galileo. Now, there is another exciting adventure regarding falling bodies. Another very exciting adventure. Supposing I had a body A and a body B on the same horizontal level with respect to the ground. And what am I going to do? I'm going to allow A to fall freely, and B, I'm going to project horizontally, like that. Now, you know the path it takes is a parabola. Indeed, this was discovered also by Galileo in the 16th century. And the question that's enchanting is this: how about their times of arrival at the ground? The impulsive notion is, well, this is going much farther and hence should take longer. But that is not true. The time of fall for A to the ground and B to the ground are one and the same. Why? Because the horizontal velocity of B remains unaltered, and the vertical velocity is taken care of by gravitational forces, the same in both cases. And here we have an experiment, a demonstration to show that. Here is a device with a spring which permits me to shoot a ball horizontally, as in the case of B, and here is one that I can release to fall freely, as A in the picture, and we will rely on our senses, hearing and sight, to verify what happens. Watch it. Simultaneity of impact. Now, this is not a proof, but it is a suggestion of the reliability of the law of falling bodies and projectiles. Consider now another one. This one has absolute enchantment. Let me put a ball in a car on a spring. And now I will put the spring in compression, drive the car away from me. The spring will be released and project the ball vertically, and the car will go horizontally, and it does no longer have the ball in it. Pretty soon, the car is over here. And what do we discover? We discover an amazing and wonderful thing, that the ball is caught by the car. And I'm going to show you that. First, let us take a look at the mechanism. Here is the cart, there is the ball, and I have compressed the spring, and it is held by a pin below. So when I pull a string, which releases the spring, the ball will be shot up. let's get over to this table and take a look at it. I'll put something down out of the way here. Let us take a look at it. Watch now, watch. I am going to drive the car away. So, pull the pin, up goes the ball, the car keeps going, and zowie, the ball is caught by the car. Watch it now. There it is. Now, I did not go so very high, and perhaps I should do that again to show you what a wonderful thing it is to witness. Watch it. Watch it. Oh, this is... There it is. And I say, this is enchanting to witness, which suggests a very important piece of physics. The horizontal motion of the car, which we would refer to as V horizontal, the horizontal velocity, is independent of the vertical velocity. Each goes its own way without interference by the other. Now, here is an experiment that I wish to talk about, but will not show you, and I suggest you try to make the apparatus yourself. I call it the monkey and hunter. Here it is. Let us take a tube, say of lucite, such as I have here, and let us bore sight on a monkey here. That's why I call it a monkey and hunter. Now, what is the monkey going to be? The monkey is going to be a tin can held up by an electromagnet. Now, what am I going to do? I'm going to put a light, say a lucite ball, in this place here, in the chamber of the gun, and I'm going to have two little wires across the end of this tube, such as I have right here. If you look carefully, I'll take that stopper out. Now, what happens? When these two wires are crossed, the electromagnetic circuit is closed and the tin can is held up. Now I put my mouth to this end in this fashion, and I blow. Now, you know what happens. The projectile emerges here. As it emerges, it opens the two little wires. The electromagnet loses its magnetic hold, and the monkey falls down. There's the monkey. Now, let's say the monkey falls to there in a certain time. And what do we expect? We expect the projectile to hit him. And here is a very important detail. The monkey can never be hit at that place if he stays there. Why? Because the moment the projectile emerges, it is taken down by gravitational forces and can never hit the monkey. That is to say, looking at it in another view, that if we had a gun aimed absolutely horizontally at a target on the nose, and we fired the gun absolutely horizontally, and the projectile emerged there, we could never hit the bullseye. Never. Why? Because the instant the projectile emerges, it is taken down like that. And as an illustration of numbers, supposing the muzzle velocity of the gun was 1,000 feet per second. 1,000 feet per second. Supposing this was 1,000 feet. And supposing under ideal conditions, the horizontal velocity of the projectile remains unaltered. It would take 1 second for the projectile to reach the target. But in 1 second, how far do gravitational forces take the projectile? As we discovered, 16 feet. Now somebody says, look here, Professor, I shoot guns and I hit targets. Of course you do, because what is really done is this. The sight on the gun is such as to compensate for this fall due to gravitational forces, and so the projectile is hit. So, remember, it is Newton and Galileo, very important in the case of falling bodies and projectile motion. Now, here is another experiment that you can do. Did we not say that when a body falls from rest, it falls successively farther? And the distance is 16 feet, 48 feet, 80 feet, and so on. I have here another experiment that you can do, and we need to take a look at an apparatus which you can make at home. It consists of a string to which are attached some spheres, and I have used billiard balls. And now, since this is pretty high, I will show you that at the bottom, the separation is closer and farther apart as we get higher. So the picture I have drawn on the blackboard is turned upside down. Now, supposing we release the whole string of things from the very top, would not the successive impacts of these balls on the ground be in arithmetic progression? Every second, let us say, one would hit, or every certain part of a second, but the distances are clearly in geometric proportion, as you see from what I have done on the blackboard. Very exciting adventures. And I must say again, this business of 1, 3, 5, uncovered by Galileo, and remember, this distance is 16 feet in the first second, in the first 2 seconds, 64 feet, in the first 3 seconds, 144 feet, and I wish to point out again, because this is enchanting to follow, this number, if we divide by 16 is 1, if we divide by 16 is 4, if we divide by 16 is 9, and you see 1 is 1 squared, and 4 is 2 squared, and 9 is 3 squared. So to quote Galileo, the distances passed over by a falling body, beginning at 0 time, are in the ratio of the odd numbers beginning with 1, 1, 3, 5. But the total distances passed over, 16, 64, 144, are in the ratio of the integers beginning with 1 squared. 1 squared, 2 squared, 3 squared, and so the next must be, of course, 4 squared, and so on. And since I have spoken about Galileo, we should take a look at this wondrous gentleman of Florence and Pisa and Rome and Padua. And here is Galileo, 1564, 1642. And I thank you for attending to our business. How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business. And our very special business today has uncommon enchantment because the motion is beautiful to witness and wonderful to understand. We are going to talk about simple pendulums and other oscillating things. Consider the following. If we have a rigid support, and there are none really because everyone shakes, however rigid, and we hang an ideal string. By an ideal string, I mean a string that has no mass, no weight, has no inertia, has no tension, is perfectly inelastic, ideal mathematically, and we hang a small bob on the end, and we displace it from this equilibrium position and let it go. It oscillates as a simple pendulum. Now, we wish to explore its motion. When you study the lesson in this business, you will find that the period, which is the time for a complete trip, comes out to be some such expression with which I will not have much to say, about which I will not have much to say. It's governed, as we see, by the square root of the length and depends upon where we time it. You know, for example, that G is one thing on the Earth and quite another thing on the moon. G is 32 feet per second on the Earth, but about 1/6 of that on the moon. As an incidental fact, matter, you would weigh, therefore, 1/6 as much on the moon as you weigh on the Earth. Now, I wish to do another pretty experiment with several pendulums. And I suppose maybe we could say pendula. This may be the plural of pendulum. Now, what am I going to do? I am going to hang up 3 of them, as I have them here soon to witness. 1, 2, 3. And how long are they going to be? This one is going to be 10 centimeters long, and this one 40 centimeters long, and this one 90 centimeters long. So the lengths are 10, 40, 90 centimeters. Notice the numbers, 10, 40, 90. I hope you get a little Q in there. There's 1, there's 4, there's 9, if we divide each one by 10. Now, I am going to set them into oscillation. And I am going to count, say, 20 vibrations of each one. Here's the way I would do it. I would set this one into vibration, starting with 0, and here is a clock which I would start and stop, and I will just run one a moment to give you the cue. I would remind you parenthetically, I am not really giving you a lecture in physics. I am merely pointing out some things that you yourself can do with your teacher and even at home. And my purpose is singularly this, to invite your interest and stir your enthusiasm and curiosity and point up at the same time the beauty and drama in these things. So I would start this 0, 0, 1, 2, 3, 4, and I would count 20 oscillations. And what would I get, probably, in this laboratory? I would get about 13 seconds. Now, where you are, say Colorado on a high mountain, you would get a different time. And if you were in Australia, you would get a different time, because little g is different from place to place on the Earth. So I count 20 oscillations, and I get 13 seconds. Now I do it all over with this one. And I count 20 oscillations. And what would I get? I would get about 26 seconds. You thinking of something? Then I would do it with the 90 centimeter one. 0, 1. Oh, I should have stopped this thing because I'm not really clocking. What's going on here? Huh? Well, there's something wrong with the... Notice now, this is the hazard we run when we depend on mechanical things. So I'm going to put the clock out of my sight. What would I do? Coming back here, somebody says, isn't the professor having a wonderful time with things going wrong? Sure they are. When you deal with nature, you must make her requirements absolutely perfect, or she will not do what you want done. So I count. I count 20 oscillations, and lo and behold, I get 39 seconds. Look, 10, 40, 90. They are in the ratio of 1 to 4 to 9. 13, 26, 39. They are in the ratio of 1 to 2 to 3. And now a marvelous thing is encountered. 1 is the square root of 1, 2 is the square root of 4, and 3 is the square root of 9. And that's what that so-called formula says, that the period is proportional to the square root of the length. And this other stuff comes out of some mathematical gymnastic. So we have learned a wonderful thing about pendulums by examining the motion of 3 of them. Now, strangely enough, when you make the exploration or develop the formula mathematically, notice that it does not contain, it says nothing about how big is the pendulum bob, how massive is it. All the period depends upon is its length. And you can show this by such an adventure as I have here. Here I have some pendula which are of identical length, let us say. Here is one made of brass, there is one of aluminum, there is one of cork, and we would find that if their lengths are identical, then their periods are identical. And that's a wonderful thing, because wouldn't you think that the heavier the bob, a different period would result? No, it does not. So we deal with simple pendula, pendulums, a bob on the end of a string. Now, anything can be a simple pendulum. Anything. Let me illustrate. Supposing you took me here, there I am, and you put a hook there in me, and you oscillated me. I am a pendulum, but not a simple one. I am a complex one. Or better physics language, I am a physical pendulum. A physical pendulum. And what is a physical pendulum? Anything that is not a simple pendulum. Illustration. Here is a metal rod. Now, if I put this on a support at one end and I oscillate it in a vertical plane, it has a certain period. It has a certain period. Now, remember, if it has a certain period, about an axis through one end, it has a certain time for its oscillation. Must there not be a simple pendulum which has the same period? Yes, indeed. A simple pendulum has the same period if it is so long. Now, how long is the simple pendulum that has the same period as this rod? Wonderful. If this rod is length L, the equivalent simple pendulum is 2/3 of L. So if I had a simple pendulum hanging here in this fashion, which was 2/3 as long as the rod, and I put them into oscillation together, they would stay in phase, meaning that they would keep step in step. So we speak of the equivalent simple pendulum as a simple pendulum which has the same period as the physical pendulum. Now, this is a rod, and this has a marvelous property. If I turn it around and put the axis at the 2/3 mark, and I oscillate it, it would be looking like this, of course, now. Here is the 2/3 mark. Here is a remarkable thing, absolutely enchanting. This rod has the same period for this axis as for this one. The same period. And hardly anybody ever believes that. But it is true, as you can discover by doing the experiment yourself. So now we explored a physical pendulum, which is a rod. How about a hoop? Here is a hoop. I have here a hoop, and I could support it by an axis about one edge, and I could let it oscillate in a vertical plane. I could let it oscillate in a vertical plane. Does it not have a certain period? Of course. It therefore has an equivalent simple pendulum. And how long is the equivalent simple pendulum? It is a marvelous thing to discover, but the equivalent simple pendulum has a length equal to the diameter of the hoop. So if you put a simple pendulum up here, which has this diameter, this length, they would keep in phase. Finally, how about a disc? Oh, a disc. Here is a uniform circular plate, and could I not support it on an axis in the manner as before, and let it swing in its own plane? Supposing, well, I better draw a new picture. We are talking about a circular disc, a uniform circular plate, and I oscillated about one edge. What is the equivalent simple pendulum? Strangely enough, the equivalent simple pendulum is 3/4 of the diameter, a matter which you can explore by making some of these things yourself. Now, in addition to simple pendula, that's a bob on a string, and physical pendula, which are bodies of any shape, like rods and discs and hoops and the like, there are many other oscillating devices. Consider, for example, a spring. Here is a beautiful spring, nicely wound, so long when unloaded. I put a load on it, and I call your attention to the beautiful motion which it executes. That has a certain period in terms of the property of the spring. Now, supposing I put a heavier load on it, a heavier load. Watch it. And I say that's a beautiful motion to experience, to witness. And now, the question, a beautiful question. Here is a spring of certain length and so stiff. Here is an identical spring which is only half as long. The question which arises is this: if the motion of this pendulum is so much with a certain load, what would be the motion of half the spring with the same load? And it is a wonderful thing to discover that it has, well, I'm not going to say. I'll leave it as something for you to explore, because I think it has much more virtue to leave some questions unanswered for you to explore than to just give you the answer. So I suggest you get a spring, indeed 2 springs, and explore their motions when one is twice as long as the other. And indeed, you will notice that I have coupled springs in different ways, suggesting that their periodic motions depend upon how they are coupled. Regarding coupled pendula, look here. Here I have a pendulum, a heavy lead bob on the end of a rod, which is pretty nearly a simple pendulum. And here is another one. And I have, as we say, coupled them by putting a spring between them. And watch the marvelous behavior. I'm going to start one. I'm going to start one and let it swing. And we will see this enchantment. Its motion will soon die out, and the other one will take up the motion. Then that one will die out, and the other one will take up the motion. And this coupling of pendulums has much to do with electric circuits, about which we shall talk another time. But watch it. This one is going. That one is going more. Watch this one stop. That has practically stopped. Now this one is going to stop. It has practically stopped, and this one is going. And so we speak of coupled harmonic oscillators. Here is another pair. Here are 2 weights on very flexible rods. If I start one, we will discover a wonderful thing, that the motion of the first one is arrested and the energy is taken up by the second one. So, I urge you to explore the behavior of oscillating bodies, and I thank you for your attention. How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business. And my business today has most uncommon enchantment. And of all the things I like to do, of which there are hundreds in this business of demonstrations, this indeed enchants my soul the most. It has to do with the principle of Bernoulli. Bernoulli. B-E-R-N-O-U-L-L-I. And I urge you to go and read about the Bernoullis, because they were an uncommon family. 120 of them, all geniuses, unlike anything in the history of the humankind. The best that we've ever had are the Bachs in music, and there were only at most 24 of those. But can you imagine over 100 people named Bernoulli, all geniuses, not one an ordinary man? Now I will recite to you quickly and passingly the principles lying herein these demonstrations, which you can read about in your books. First, we learn from Bernoulli that when a moving fluid like air encounters a constriction, that is a narrow space, the velocity increases. So as we say, the velocity is increased in a constriction. One other principle emerges from a study of Bernoulli, and that is that the pressure in a constriction diminishes, or goes down. So we have these 2 principles. Velocity increases, pressure diminishes in a constriction. And now I'm going to show you an abundance, an array of experiments, demonstrations that reveal this. Consider the following. Why an airplane can fly, says Bernoulli. He explains why. Why a ball can be thrown in a curve. Why a chimney has a good draft. Why a bird can soar. Why a boomerang, whatever it does, boomerangs. All of these things can be accounted for in terms of Bernoulli's principle. Here is a magazine opened so that the pages are curved in this way. And now I'm going to blow a stream of air against the inner edge of these pages. One would think that they would be pushed down by the push of the air. But no, watch. Watch. Well, the page was lifted up. There it is. Now, that airplane wing has some flutter, which we don't want, of course, in a real airplane wing. But the air going over the top gave rise to a diminution in pressure, and the atmosphere below lifted the page up. Consider another of the same. Here are two spheres, two croquet balls, with a little separation between them, and this region is a constriction. I'm going to blow some air through there. One would think impulsively that the spheres will be blown apart. No, they are not. The pressure will be reduced and the atmosphere will push them together. Watch it. There they are, pushed together by the greater atmospheric pressure on the outside. Now, of what consequence is this? Well, very important indeed, because if two ships pass, let us say, two ships passing on the sea, if they pass too close to one another, the pressure is reduced between them and they could be made to collide and break apart. Here is another, very dramatic, my chimney effect. Here I have a chimney. You remember a requirement of our work together is imagination. So I could, of course, draw the picture of my house and my chimney, and there's the fireplace in my house. Now, why does my chimney have a good draft? It has a good draft if there is a stout wind blowing across the top of the chimney. Why? Because high velocity, diminution in pressure, the atmospheric pressure pushes the smoke up the chimney. I'm going to prove that. Here is my fireplace. My fireplace is a vessel with some puffed rice. Here is the chimney. I'm going to blow a sharp stream of air across the top. The pressure will be reduced here in this region. The reduction in pressure will be felt in the tube, and the atmosphere will push it up. Watch it. There it is. My chimney has an extraordinarily good draft. Watch it. There it is. I say that's a terrific chimney. Now, here's one that's even better still. Here's a funnel. And I'm going to put some puffed rice in that funnel. And then I'm going to blow some air through that funnel just to show you that air is blowing out of that funnel. Watch it now. Whoop. Oh, well, of course, there it is. Sure, the puffed rice couldn't have come out unless I blew it out. Now I'm going to put a ping pong ball in there. There it is. Now I'm going to blow that ping pong ball out. Watch it. Indeed. Somebody says, oh, he's got it stuck in there by magnets or something. No, no. I will dispose of it as quickly as I can with the following remark. Here it is. Here it is. Here is the funnel. There is the ball. Here is the air. The ball fits in the funnel very snugly, and these regions right here are constrictions, and when the air passes in there, it has a high velocity and a reduction in pressure, and the atmosphere holds the ball up. Indeed, this principle of Bernoulli is why an atomizer works. You know what an atomizer is. An atomizer is a tube that resides in a vessel, and here is some liquid, and here is a tube across here, and here is a bulb, and you squeeze the bulb, air rushes across, there is a reduction in pressure, the atmosphere pushes the liquid up, and then the liquid is caught in the airstream and comes out there. I have often thought that the reason that's called an atomizer is because little atoms of the liquid come out there. Don't you like that idea, little atoms? Now, here is an atomizer, and spray would come out there. Now, I'm going to show you an atomizer on large scale. Watch it. This is fantastic. Here is a tin can, and here is a tube quite like that one residing in the atomizer. And I'm going to blow a stream of air through this tube. There will be a reduction of pressure in the tin can. And now what will the atmosphere do if the can has less pressure inside? The atmosphere will collapse it because it is enormously strong. Watch it. Watch. There it is. There it is. I tell you, that's terrific. It's so terrific, I'm going to do it again with another one. With another one. Yeah, why? Well, if I like it, I'm going to do it twice. I may do it 3, 4 times. Watch it. Oh, look at that. Well, that's 2 times, and I'm going to do it once more. Once more. Why? Because I like it. Watch. Whoop, whoop. Oh, oh, there it is. Notice, there it is. Wait. There it is. There it is. And I tell you, that's terrific. That's fantastic. Now, pressure reduced in a constriction, velocity increased. Consider a consequence. Flag. United States flag, Australian flag. Why does a flag flutter? Bernoulli. Have you not heard sometimes your Venetian blinds chatter? Bernoulli. The air blowing across the top of the shutter gives rise to a reduction in pressure. The shutter is lifted up. Now, because of its springiness and its inertia, it falls back, and so it oscillates. And I'll tell you how powerful an instrument Bernoulli's principle is. Some years ago, a bridge way up in northern Washington collapsed because of the effect of Bernoulli's principle, because of the role Bernoulli played. Now we got something wonderful. Terrific. Oh, why is it terrific? Because you would not believe it. Here it is. Supposing I had a tube, and I drove a stream of air up here, and I had a ball right at the top, vertically above the blowing air. You would say if the ball stays there, it's because the air pushes up and the ball pushes down, and when they are equal, the ball stays there. And that would be correct. But now supposing I turned the tube off the vertical, and the ball still stayed there. Well, you can't say that anymore, because when the ball receives the air that way, there is a component that way and a component that way. That one may hold up the ball, but this one should drive it away. But I'm going to show you that it doesn't. Watch it. Oh, oh, little trouble. Uh-oh. Let me try a heavier ball, a golf ball. And I call to your attention a very significant feature of this. The ball was spinning. This spin gave rise to a reduction of pressure on the upper side, whereupon the atmosphere held it up. Let's take a big one like this. Styrofoam ball. Watch it. I hope we have air enough. Watch. And I say that's terrific. I just love that. I want to do it again because I do. Any objections notwithstanding. Question, could I get that ball on the horizontal? That's a good one to explore. Indeed, you can do this by going to your gasoline station and using the air hose at your service station. Let me do it again with a golf ball, which is quite heavy. Golf ball, quite heavy. Oops, little trouble. Now, finally, since I enjoy, as you know, the physics in toys, here is a wonderful demonstration of Bernoulli. Here is a little toy car. Here is a little toy car. And what am I doing? I am storing some energy in a wound-up spring. And when I release the spring, It unwinds and turns a fan, and there is a stream of air emerging from here. I'm going to show you that there is. Watch it. There is a little polystyrene ball. There it is. Now remember, I can put that off the vertical. Watch it. There it is. Now what I'm going to do should be an enchantment for ages 4 to 94, as all the physics that we do should be. Watch it now. Watch. Oh, isn't that something? Look at that. I want to do that again, because I like it. There it is. This is a Bernoulli car, and why does it work as it does? Because, one, there is a push of the air, a high velocity on one side of the ball, which gives rise to a diminution in pressure, and thereby the atmospheric below holds it up. Now, what shall we say about Bernoulli? The applications are phenomenal. As I've remarked, two ships passing on the sea should not pass too close to each other. Indeed, have you not stood on the sidewalk when a fast-moving vehicle has gone by and you have been made to rock? Or have you not passed in your car, a bus, let us say, and your car is made to rock? This is a consequence of the reduction in pressure between the vehicles, whereupon the atmosphere on the outside pushes them together. Indeed, when the Japanese designed their most recently accomplished railroad from Osaka to Tokyo, where the trains go about 120 miles an hour, what was the critical thing? Several. One, the center of gravity idea. Number two, how close can the cars be without the effect of Bernoulli? And so I say, read about the Bernoullis. They are wonderful to know about. And I thank you for your attention.